All right, so welcome to our presentation on gearboxes. If you are in this Zoom meeting, it'd be best if you turn off your camera so that you don't have to show your face on YouTube unless you don't want to. All right, so let's get started. Gearboxes, what they do and how they do it. So this presentation was actually mainly created by one of the mentors on my team, but I will be presenting it in his place. My name is Jessica, and I'm a senior student member on the 2702 Rebels. And today I will be giving you guys a complete introduction on gearboxes. We'll cover some of the different types of gearboxes, some of their characteristics, and a few calculations that go alongside with them, as well as what a gear train is. So let's get into it. Let's answer that question first off. What does a gearbox do? Well, the primary purpose of a gearbox is to transfer power. So in that image on the right, we can see that we have our input of power, which is provided by our motor, that little black component there. And then the power is transferred through a gear mechanism that you can't see, but it's within that yellow container. And then the power gets transferred to an output shaft, which likely will be used to turn a wheel, for example. While you're transferring that power, there's some things you can do. For example, you can increase or decrease the rotations per minute, RPM, or the torque. Rotations per minute you can think of as speed, and torque is essentially rotational force. If you don't know what torque is, don't worry, we'll cover that later on in this presentation. You can also change the direction of rotation, so clockwise or counterclockwise. And you can also change the axis of rotation, and you can think of the axes of rotation as this line that goes through the center of something that's rotating, in which a part or an object rotates about. Some secondary purposes of a gearbox are to provide mounting for motors and wheels and other mechanisms, which is definitely being used in the example to the right. You might also use a gearbox as a containment of lubricant, which basically means that you can put lubricant inside of your gearbox, and that will, of course, make it so that you're reducing friction and the parts can move around more smoothly. And by reducing friction, you're reducing the amount of energy that is lost as heat, which makes the mechanism more efficient, since more work is going in, or more of the energy is going into your work, what you want it to do. You can also prevent backdrive using a motor. And backdrive is basically when your mechanism goes in reverse. So usually that's the direction you don't want it to go. For example, if you're lifting something and then when you stop exerting power, load is a little bit too heavy and it starts to fall, a gearbox can help reduce that or prevent it using the friction between all the different components and parts in it. And of course, you can also change the location of the axis of rotation, which we'll see in the different types of gears that we look at. So there are many different types of gears that can be used to transfer power. You'll have to look at which one you want to use for your specific purpose. So starting off with the simplest gears that we know and the most common that you'll see in FRC, spur gears. These are basically discs with teeth that go around the outside of their perimeter. You'll notice that spur gears have to rotate or mesh on the same plane or at the same level, which is also called a stage. And you will also want to remember that the rotation is, you can say, flipped for two interlocking gears. So for example, if your input gear, that first one on the left, was going clockwise, then the gear that's meshed to it, like maybe your output gear, is going to move counterclockwise. So it swaps each time they mesh. So our next type of gear is beveled gear. And this will change the axis of rotation by 90 degrees. So if you can imagine an axis going through each of those gears, you'll notice that they go perpendicular to each other. So the axis of rotation has changed by 90 degrees. We also have worm gears. These also change the axes of rotation by 90 degrees. So again, if you imagine an axis of rotation going through each of the gears, so for that first round one, it's going to go kind of out of your screen, and for the other one, the axis of rotation is parallel to it. So again, those two things are perpendicular at 90 degrees to each other. Another interesting element of it is that it can prevent or at least reduce backdrive, and that's mainly because as you can see in the image, that worm gear has a lot of points of contact with the other spur gear, and so there's more friction, of course, more of the parts are in contact, and thus it is easier to prevent, the gear from slipping or going in the direction you don't want it to. But a disadvantage of this friction is obviously that we lose energy from the friction as heat energy, and thus the gear becomes less efficient. So continuing, actually, I wanted to show you guys a few GIFs of these gears because I think seeing them in action will kind of help you understand how they work. So here we have our spur gear. You'll notice the first one's going clockwise and the other one's going counterclockwise, yeah. All right, so this next one, okay, there we go, sorry. So this is a bevel gear and very helpful. It gives us the axis of rotation, so you can see the axes of rotation are perpendicular to each other. It's hard to, okay. I have to scroll for this one. So, and this is our worm gear. So you can see with this animation that there's definitely a lot of points of contact, a lot of points of friction, and which is characteristic of the worm gear. Okay, back to the different types of gears. So our next gear type, rack and pinion. So this one is very unique because it's one of the only gear types that we'll see here that can convert rotational motion into linear motion. So you see that pinion, which is essentially a spur gear with a shaft that's going through it. When you rotate that pinion, that's going to cause the rack, that long rectangular piece, to move forward when it's turning in one direction. And then if you turn it in the other direction, it's going to move backwards. We also have the internal gear. And so in the image to the right, the internal gear is referring to that green gear only. So internal gears, they're mounted around the perimeter and their teeth are on the inside of that perimeter. So what are internal gears usually used for? They're often used in planetary gearboxes. So planetary gearbox is composed of both internal and pinion gears. So in the image, you can see we have on the outside an internal gear, and in the very center, we have pinions, and then surrounding or between those two gears, we have what we call planetary gears. So you can think of this kind of as a solar system, where those planetary gears are basically orbiting that sun gear in the center, and usually the sun gear and the internal gear will be stationary, so that's kind of why we call it a planetary gear system. And planetary gear systems usually come in multiple stages, as you can see in the image, and the benefit of that is that we can get a gear reduction from that. And so we'll cover that very shortly, but just keep that in mind. All right, so let's cover some important characteristics of gears. So one of the simplest characteristics that you can see on a gear is the number of teeth. You can get the number of teeth by counting the number of teeth around that gear. I don't think you want to, but I'll give you the number of teeth for both of these gears, 15 teeth and 30 teeth. And an important thing to note is that the ratio of the number of teeth on each gear in a gearbox will give you the gearbox reduction. So what does that mean? For example, you see that first gear, the 15-tooth gear, when it's turning the 30-tooth gear, for example, if it's like the input gear, that will provide a speed reduction of ratio of 30 to 15 or 2 to 1. What that basically means is that as you're turning that input gear with 15 teeth, it will have to make 2 rotations for every rotation of the second gear, right? 15 times 2 is 30 because we're always moving one tooth at a time. And that will give you a reduction in the speed or the rotations per minute. Another characteristic that you'll see often is the pitch or modulo. So the pitch can be calculated can be defined as the number of teeth per inch of pitch diameter. And pitch diameter is a predefined almost circle or diametral position on the gear, which I'll show you in an image shortly. But for example, if you have 15 teeth on a gear and it has a 32 pitch gear, or has a 32 pitch on that gear, then you can figure out that it has a pitch diameter of 1/2 inch, right? So 16 teeth divided by the pitch diameter, which is half an inch, will give you 32. And likewise, you can calculate the outside diameter of the gear. So the outside of the entire gear. So if you had like a circle that just fit that gear, you can calculate the diameter using this equation. So the number of teeth plus 2 divided by the pitch diameter. So for this 32 pitch gear with 16 teeth, we take 16 plus 2 gives you 18, and then divide that by 1/2 inch, which is the pitch diameter, which will give you 36, if my calculations are correct. And another important characteristic is pressure angle. And so that is defined by the shape of each tooth. So the shape of the shape of the teeth on a gear can change the pressure angle. And you should note that gears that mesh should have the same pressure angle. So if you're having 2 gears and they're meshing, make sure they have the same pressure angle. All right, let's look at a diagram to kind of visualize what we just discussed. So for example, that first label, the outside diameter, like I said, if you took a circle and it just touched the tips of all those teeth on the gear, and then you took the diameter of that circle, that would give you the outside diameter. And then you can also see outlines of the pitch diameter. So again, it's a theoretical value, so it can't actually be measured, but it's used to determine the measurements of other values, like the pressure angle. So the point where those 2 pitch diameters touch, we call the pitch point, and the pressure angle can be measured at that pitch point. So bear with me, but the pressure angle is essentially the angle between the tangent, or the line that's perpendicular to the surface of that tooth at the pitch point, and the line that is tangent to the pitch diameter at the pitch point. You don't have to memorize that, but in case you were wondering, that's how pressure angle is defined. All right, so like I promised, let's talk about torque. Torque defines the strength of the rotation, or you can think of it as a rotational force. So in the image at the top, we see that we have a weight, and it's bearing down on this, what should I call it? A plank connected to a point of rotation. And so you can measure the torque by multiplying the length of that plank and the force to get your torque. So you can also think of the length as like the radius of your circle of rotation. And as you can see from the equation, torque would be proportional to the distance that the force is applied to from the axis of rotation, or from the point of rotation, you could say. It's also proportional to the force you exert. And torque is measured in inch pounds, or feet pounds, or inch ounces, or Newton meters. Either way, note that it's a unit of distance multiplied by a unit of weight. Newtons is how weight is measured in the metric system. And so let's look at an example. A shaft producing a torque of 100 ounce-inches can support a 100 ounce weight on a shaft that is 1 inch in radius, or 2 inches in diameter. So you can see in that second image, we have this circle that's meant to represent the diameter of your rotation, so where a point would rotate around. And the radius of that circle of rotation is 1 inch, and the weight the weight of that is being borne is 100 ounces. So the force times the length, 100 ounces times 1 inch, is going to give you 100 ounce-inches, which is a torque. Also note that a gearbox, which provides a speed reduction, remember when I talked about the ratio of the teeth on each gear? So a gearbox that has a speed reduction, different gears with different numbers of teeth on each, will create an equivalent increase in torque. So if you're reducing the speed, then torque is going to increase. Vice versa, if the speed is being increased, the torque will have to decrease. And so if you want to know the reason for that, you can look at the equation. Power equals torque times speed, or rotations per minute. And if you remember, bear in mind that power is energy divided by time, right? So, and energy has to be conserved, therefore power also has to be conserved. So if you want your input power to be conserved, or sorry, if you want power to be conserved, then your input power has to equal your output power. And that means that if you end up increasing the speed through your gear mechanism, you're going to have to decrease the torque so that when you multiply those two values together, it still equals the same amount of power. Or vice versa, if you are decreasing the speed, you're going to have to increase that torque proportionally, of course, so that the power remains the same throughout. Let's look at a few alternatives to gearboxes in case gearboxes aren't your style. So we have the sprocket and chain mechanism. So each sprocket, the teeth on the sprocket will mesh with the links in the chain. So as you can see, each sprocket, it kind of looks like a gear, right? The only difference is that sprockets aren't exactly meant to mesh directly. They're designed to mesh with these chains that go between them. And like a gear, though, the ratio of the number of teeth on the input sprocket to the output sprocket determines the sprocket reduction, I suppose you could say. Oh, I should also note that each turn, like each teeth that moves on one sprocket will also be one tooth that moves on the other sprocket, like gears. All right, belts and pulleys are another way that you can replace gearboxes. So there's two main types that you might see in FRC. The first one is called timing belts. And so these belts have teeth on them, or little grooves that these pulleys, which are the round circular things with the little grooves in them as well, kind of cling on to. And so like the sprocket, each turn in the groove of the pulleys is going to turn the other one by the same amount. And the second type of belt and pulley is the more traditional, the V belts, which you can see on the right. And the reason they're called that is because they mainly rely on friction to transfer power. So there's like no grooves on it. It's completely smooth, but usually it's made out of a material that has enough friction to transfer that power. And for belts and pulleys, the ratio of the diameters determines the reduction. So you're always kind of looking at the circumference in a way. And here's the picture to zoom in if you couldn't really see the grooves on that timing belt. So there's those little grooves, and they align with the little grooves in the pulley. And of course, these ones also have to have their pitch diameter and their outside diameter. And again, pitch diameter is a theoretical predefined value. All right, so a lot of content was just drilled into your minds. So why don't we start off with a little example to kind of put things into perspective. So this is a simple gearbox. I mean, it's simple to most gearbox experts. The output shaft, the large gear, would turn half the rate as the input shaft and would have 2 times the torque. And the reason for this, if you've already caught on, is the number of teeth. So you don't have to count, but let's assume that first gear has 16 teeth and the second gear has 32 teeth. So the first gear is going to have to turn 2 times for every, or 2 rotations for every rotation of that second gear, which gives it a gear reduction of 2 to 1. So the speed of the first gear is obviously 2 times as fast as that of the second gear. So if the speed is doubled, we're going to have to reduce the torque by half on the second one, or on the first one, sorry. And that is why the second gear will have 2 times the torque as the input one, which is faster, but has less torque. And the second one is slower, but has more torque. So you're increasing the torque as you reduce the speed. Also note that bearings are often used to reduce the friction of the input and output shaft. You can see all those little balls are very slippery, wouldn't really create too much friction. And so that's very useful when you're designing a mechanism to include bearings. All right, how about a more complex example? So a multiple stage gearbox, or also called a gear train. So you can see there's multiple stages. We have gears on different levels, meshing at different heights or levels, whatever you want to call it. So the output of one stage drives the next. So the first stage is composed of, I don't know if you can see my mouse, but that first gear at the bottom and that second larger gear at the bottom. And then the second stage is composed of that third smaller gear that's sitting on top of the second one and the fourth gear that's meshed with that. And as you turn the first stage, because the second and third are on the same shaft, they're going to turn together, and that drives the second stage. Each stage reverses the direction of output. That goes back to what I said about clockwise and counterclockwise with spur gears. So maybe you can follow through with me, but let's say we're turning that first gear clockwise. The second gear meshed with it is going to turn counterclockwise. And because that third gear is on the same shaft as the second one, they're going to turn the same direction, so also counterclockwise. And then when the third one meshes with the fourth one, the fourth gear is going to move clockwise again. So basically, you can think of these two gears as like the same direction since they're on the same shaft. So it's clockwise, counterclockwise, and then clockwise again for each of those shafts. This also provides a higher reduction in less space, and the reason for that is because reductions can multiply. So for example, if you had a 2-1 reduction on one stage followed by a 4-1 reduction on the second stage, then you can multiply those together to get an 8-1 reduction in speed. So 2 times 4 is 8, and 1 times 1 is 1. And that's much easier than if you had those gears all aligned. So you had, for example, one gear that had a certain amount of teeth, and then the second gear had 8 times the number of teeth. It's going to be a lot larger, and it's going to be taking up a lot more room. Or even if you just had, actually, I guess it wouldn't work if you had like 3 gears. Sorry. Anyway, higher torque stages may need stronger gears, shafts, and bearings. Just a design note. You might want to keep that in the back of your mind. All right, so now a question for you. I know I've been talking this whole time, but time to get your gears spinning. How might you get a 100 to 1 speed reduction? That is the question. So that brings us to our activity. I'm going to exit out of our presentation, and I have a few links here for your benefit. Let me close all these tabs. I just realized I forgot to show you guys the other gear systems, right? Sorry about that. So here we have a planetary gear, seeing in action. See, the center gear is stationary, the outside gear is stationary. Stationary is it still rotates, but it's stationary in its position. And these planet gears just orbit around it. And then here we have the internal gear, the less interesting planetary gear, where it's just the internal gear and a pinion. And of course, the rack and pinion. So you can kind of better visualize how rotational motion can be turned into linear motion this way. Oh, now I can't see anything. All right, so here's our first simulation, and this one, I don't really have an activity associated with it, but this is what the URL looks like. I think if you just search up like gear simulation, you can see it. But it's just a good example that you can kind of play with and kind of see how planetary gears work, because they might be one of the more complicated ones that I showed you in the types of gears. So in the simulator, you can change the number of teeth on the sun gear, right? And then subsequently, you're going to have to change the size of the planet gears, right? So they fit, because they got to touch. If they're not touching, then you can't really orbit. Or you can change the number of planets. Usually we stick to about 3 or 4, maybe 5. but I don't think we've ever, I don't think I've ever seen a Planetary Gear stage where it was just 2 or 1. And then if you think about it, you could have these multiple stages stacked up on each other, and that will create a gear reduction, just like the spur gears, but instead of going by stages in a sideways manner, they're just directly on top of each other. It's very nice and compact and easy to design around. And you can change the ring teeth, so you can change the teeth of all these things. And then you can also change the speed. And that's obviously going to influence how the other gears rotate. So you can play around with this. I won't stay too long on it, but I think if you're interested, the catalyst.com gears, or just search up Planetary Gear Simulator. Okay, so the activity that I actually wanted to show you guys is called geargenerator.com. And so this is what we're going to use to kind of figure out that first question that we have, how to get a speed reduction of 100 to 1. So let me show you, let me just quickly go over how this kind of works. So animation speed, we don't really care about that. You can play with it if you want to be, if you want to have fun, I guess, because you can change it, you can make them faster, make them really fast. Anyway, we won't play with that, but we will play with our connection properties. Okay, so here you can add a new gear. So right there, I added a new gear. You can remove the gear. You can't clear it just yet. Parent gear. So if you select a different each gear, you can change its properties. So you can change, remember, number of teeth, pitch diameter. You might not want to mess with that, but pressure angle, all those things. So you might want to stick to number of gears for simplicity's sake. If you select this, it becomes an internal gear. So I just turned that one into an internal gear. It looks kind of weird. If I deselect, it's no longer an internal gear. And there was something else. Something about parent gears. Let me add one. Okay, let me maybe let me clear. Okay, nice and clean. So I remember somewhere you can, if you add a new gear, so now we have the second gear, and then axle connection. All right, that's what I meant. So now you see we have 2 stages here, or here. What's more realistic is if I add one here, and then I say axle connection to that one, and now we have, well, it's kind of hard to see because they have the same number of teeth. So now we see they have an axle connection, which basically means they're on the same shaft, just like when I showed you, oh, not that one. When I showed you this, so they're on the same axle. They're just like gear number 2 and 3. So if I select that one, I can add a new gear on this stage. And now look, we've created a multiple stage gearbox, or a gear train, which I should get used to saying. Okay, so a 100 to 1 gear reduction. The first way that you could go about this, which I would prefer you didn't, but if you really want to, you can do just one stage. What does that mean? Well, we're going to have to start with a gear. So this one has 10 teeth. And to get a gear reduction of 100, what are we going to need to do? We're going to need to have to create a gear with 100 times as many teeth, so that this first gear will have to turn 100 times for every rotation of that second gear. So let's do that, I guess. Well, I don't know about you, but I don't think this would fit in any FRC robot that I've ever seen. So let's not, oh, I did 400 too, there's a limit. Let's not do this method. Let's instead invest in the idea of what? A gear train. So we're going to have to consider changing maybe the number of teeth. There's a limit of 100. Okay. All right, so with this as a reference, let's try and create a gear reduction of 100 to 1. So what 2 gear reductions could we multiply together to get a gear reduction of 100 to 1? think about that real quick. I'll say the answer in a second. How about a 10-to-1 gear reduction for the first one, and then on the second stage, we can have another 10-to-1 gear reduction, and when we multiply those together, we're going to get a gear reduction of 100-to-1. So let's try that. Let's add a new gear. We're going to give this guy 10 times as many teeth, still a lot, I know. And then on this one, we're going to add a new one. I bet we can't even see it at this point. Okay, we can kind of see it. And we're gonna make it have an axle connection, so now it's on a new stage. Ah, there it is. And then to this one, we're gonna connect it and give it a number of teeth of 100. All right, wish I could zoom out. I don't exactly remember how. And so now, if we were to start this, so this is going to, so we have 10 gears here, 100 gears here. That's going to be a gear reduction of 10-to-1. This is turning at the same speed. And we're going to have a gear reduction of, again, 10-to-1 because 10 gears, or 10 teeth, 100 teeth. So we start out with this speed. We end up with this very slow speed. If we increase the speed, maybe it'll help you visualize. So we're spinning that fast there. We're only spinning this fast here. So you can see that we've reduced the speed by 100-fold using this gear train. Much more, well, I guess it would fit better in an FRC robot, but still not really desirable. I mean, you might want to use more stages, so maybe have 3 stages instead of 2, but I'll let you experiment with that on your own. Maybe you can end up with a more pleasant looking gear train than I've created. Yeah, so that concludes this presentation on gearboxes. I encourage you to play around with this simulator, try and make gear reductions of your own. Just, I don't know, if you really want to create crazy numbers like 500-to-1 or something, or try maybe odd ratios like 80-to-6, perhaps. Actually, that's not 80-to-3. There we go. We can't further reduce that ratio. And see, this is basically the closest we'll get to creating gearboxes in this current pandemic. So try it out. And I hope you enjoyed this presentation on gearboxes. I